Welcome back. In our last explainer, we looked at the mechanical theory of the HPA circuit breaker. Today, we are taking that theory and throwing it right into the wild, unpredictable world of marine environments. We're picking up exactly where we left off, bridging that gap between textbook mechanics and real-world sea conditions.
So, remember the puffer mechanism? We talked about how it acts like a high-speed bicycle pump, blasting ionized SF6 gas to snuff out an electrical arc in literal milliseconds. But here is the catch, and this is what we really need to master today. That mechanism only works safely inside a very narrow, highly specific pressure window.
Section 1. Pressure versus ambient temperature. The shifting variables. Okay, let's dive into this. Because as you know, out on the water, temperatures are all over the place. Whether you're freezing in the North Sea or sweating it out in the Gulf of Mexico, the heat of your environment absolutely dictates the gas pressure inside that sealed breaker pole. You can't just memorize one number and call it good. The standard filling over pressure is 2.5 bar? Sure, but that's precisely calibrated for 20 degrees Celsius. As a marine engineer, you've got to recalculate based on the ambient heat. If it drops to 0 degrees, you fill to 2.3 bar. At 10 degrees, 2.4 bar. At 20 degrees, there's our standard 2.5. But if you're in a sweltering room at 30 degrees Celsius, your target climbs to 2.6 bar. The gas shifts, so your targets have to shift with it.
Section 2. The 2.0 bar alarm, the absolute limit.
Now, while temperatures and fill targets bounce around, the absolute safety limits of this breaker absolutely do not. There is a hard floor here, and that limit, it's 2.0 bar. If the pressure drops to this exact single number, a density relay immediately triggers a system-wide alarm. It's the absolute lowest safe operating pressure.
Let me be super clear about this. That 2.0 bar threshold is not a mild suggestion. It's a hard, non-negotiable safety boundary. It is literally the line between function and failure. Below 2.0 bar, the pole just cannot guarantee fault interruption anymore. If an arc strikes at, say, 1.9 bar, the puffer cylinder simply doesn't have the SF6 density required to blow the arc out. That means a localized fault could easily escalate into a catastrophic switchboard fire. And nobody wants that. Section 3. Maintenance and overhaul. The dual clocks. And this brilliantly illustrates why maintenance requires such strict discipline. You're basically managing two separate timelines, two concurrent clocks ticking away on every single HPA breaker. First, you've got your gas checks. These are operations-based. You verify pressure at commissioning, then after 7,500 operations, again at 10,000 operations, or obviously immediately if that density relay alarm sounds. Then you have the mechanical operating gear overhauls. These have inflexible, hard limits. You have to overhaul the gear after 5,000 operations or every 5 years, regardless of how little it's been used, or after a maximum number of short-circuit breakings. Whichever of those three hits first, boom, you pull the breaker for overhaul. Section 4, Knowledge Check. The commissioning scenario. All right, let's put this into practice. Imagine you're an engineer standing in a sweltering switchboard room. Let's see if you can apply these rules on the fly. Here's your scenario. You're commissioning an HPA breaker. The ambient temperature in the room is 30 degrees Celsius, and the pressure gauge reads 2.5 bar. Think back to our numbers. Is this breaker correctly filled, or is it underfilled? Take a second and lock in your answer. If you guessed underfilled, you hit the nail on the head. Remember, 2.5 bar is only the correct target if the room is sitting at a comfy 20 degrees Celsius. Because it's a hot 30 degrees, the gas should naturally be exerting 2.6 bar of pressure. So, signing off on a 2.5 bar reading at 30 degrees means your gas density is dangerously low, and that breaker needs topping up with SF6 before you can even think about calling it sea-ready. Section 5. Conclusion. Certifying the breaker. So, the crucial point here is that understanding this dynamic relationship between temperature, pressure, and strict maintenance schedules is exactly what separates a junior operator from a principal engineer. You've just locked in 3 highly specific skills from this explainer. You can correct SF6 fill pressure for literally any marine ambient temperature. You know exactly how to recognize and respect that absolute 2.0 bar density relay alarm, and you can accurately schedule the dual clocks of gas checks and mechanical gear overhauls. That is the whole shebang for keeping this breaker certified and safe for its entire service life. You now know exactly how a single breaker behaves, how it survives a fault, and protects its immediate circuit. But here's a wild thought to leave you with. If one single breaker is this complex, how in the world does an entire power plant of multiple massive generators share a dynamic load and stay perfectly stable together without completely tearing the electrical network apart? Well, that's exactly what we're going to uncover in our next explainer. Until then, keep learning and stay curious.